everyone, and welcome to the first Biogas Masterclass hosted by the World Biogas Association in partnership with our wonderful Danish colleagues from Biogas Goes Global and the Food and Bio Cluster Denmark. So your chair for this session on pre-treatment solutions for biogas production, food waste, straw, sand and grass is Chris Bohl, Head of Waste, Recycling and Biogas and Advisory with the Danish Trade Council in America. And for those of you who are not members of the World Biogas Association, you can find out more about us and what we do by contacting John Hughes in the chat or by following the link that we will post in the chat.
Thank you, Cheryl, and good morning, afternoon, evening to everybody who is joining today. As Cheryl said, my name is Chris Bohl, and I'll be moderating and chairing today's session. I am only going to take a few minutes with some introductory remarks, and then we'll get into the better part of the program, the great slate of speakers we have to share some of the experience from Denmark on pre-treatment solutions. I want to say thank you to the World Biogas Association for co-hosting this event along with Biogas Go Global. Specifically want to thank Cheryl Morton for her leadership of the organization, and Cheryl, Edward, and John for working together, especially with Michael Steckler from Food and Bio Cluster Denmark, who came up with today's list of presenters. As Cheryl said, we'll try to get to as many questions as we can today, either by answering them online or in person if we have time. Next slide, Cheryl. Very quickly, the share of renewable natural gas in the Danish gas system, as you can see from this graph, has been growing immensely over the last 10 years especially. All of this renewable natural gas in Denmark is based on biogas from manure, food waste, and other organic waste streams. Next slide. A primary reason for this very exceptional growth in biogas and renewable natural gas is the Danish biogas model, which is very much predicated on the co-digestion of different organic waste streams. I'm not going to get into the graphic there, but as you can tell, this system is based on animal manure from both cows, pigs, food waste from urban centers, food production wastes from food manufacturing, and other agricultural residuals. And you'll hear a lot about that from our speakers throughout the remainder of this webinar. Next slide, please. You've heard the term Biogas Go Global. Cheryl mentioned that. Biogas Go Global is a program, and now in its third year, that was sponsored by Industriens Fond in Denmark. It is a partnership between the Trade Council of North America, for whom I work, Food and Bio Cluster Denmark, Innovation Hub in Denmark for moving forward many different sectors, including biogas, and the Danish Energy Agency, which has a strong role in the policy and financial incentives that move biogas projects forward. The goal of this program is to grow partnerships and knowledge sharing across the biogas sector, not only in the US and Canada, but throughout the world. And it's based on a triple helix approach of involving academia, the private sector and industry, and government. Next slide, Cheryl. Again, these are a couple of the publications that Biogas Go Global has put out. There's a lot of other information on the website. I invite you to visit biogasgoglobal.com, and you can see links to much of this information. Next slide. Here in the US, my colleague Cecilia Sorensen and I represent a number of Danish companies that make up a biogas alliance. You'll hear from several of those today, not all of them, but if you have any interest in any of these other topics, please feel free to reach out to me or somebody within Biogas Go Global after the fact. Next slide. Here's my contact information, as well as that of Klaus Mortensen, who's the director of the Biogas Go Global program. Klaus works for Food and BioCluster Denmark. So please feel free to reach out. Our first presenter today is Carl Jorgen Nielsen. Carl is a project leader at Planergy. Carl has 12 years of experience as a project leader at the company, and this has included planning and tender of biogas plants and optimizing them with pre-treatment systems. Prior to that, Carl has 16 years of experience as a technical advisor for the Danish Agricultural Association. And Carl's going to provide an overview of some of the mechanical and biological methods of pre-treatment. Carl, thank you for being here, and the floor is yours.
Okay, thank you very much, and thank you for the opportunity to speak a little bit about, to give you an overview about the pre-treatments methods that we are using in the Danish biogas plants. I have some topics. I'll start with talking about the pre-treatment systems before feeding into the digester. We'll talk about some inline treatment, which is pretty new in Denmark, and treatment of the degas digestate with separation, and also we're using reuse of fiber fraction, and some biological pre-treatment where we are making silates. The first one I'd like to tell you about is the system with mainly for deep litter. We have an automatic crane and a pre-treatment systems, and it's also used for grass and maize. It's a biomixer in connection with a BHS biogrinder and a power feed from Robe, so we can feed it into the digesters. The power feed system is it's a little bit sensitive to the feedstock if it is too wet or too dry. So if you get some very wet deep litter into the feed in as feedstock, we have to mix it with some more dry feedstock to get the right dry matter content. This grinder system is also equipped with some iron magnets to collect the iron before it enters into the grinder. But we still have the problem with the stones, and stainless steel is still a challenge. But normally in this biogas plants, the stones and stainless steel will be caught in the biomixes that you see here close to the crane. So that's where we have the problems, and not in the grinder. But deep litter is always with a lot of stones, normally in Denmark. We also have a lot of focus on premix systems in several Danish biogas plants. Here we have it in a directly connection with a big mix system from Robe, and in this plant it's used for grass, maize, deep litter, and straw, and it mixes the dry feedstock with the digestate from the biogas plant from the digester, and we have about 10 to 12% dry matter in the digesters in the Danish biogas plants, where we have a lot of dry feedstock. And if you see in this picture here below, you can see there's a big area around the premix systems, and there's also a crane, and I think that's very good because there is some maintenance in the premix as in all the other pre-treatment systems. So we have to change the bearings in the pumps and also in the premix systems. And we also have to have the stones. This one is with an automatically stone trap, so the stones they are collected into this. We have a sieve here, and the stones will be collected in that, and the liquid part will be pumped away from this this hole in the ground and out through the big mix, so it'll take a new turn. So, but it's very important that you get the system, so it's very easy to operate. But this system is, I think we like it because it can take almost all kinds of straw and deep litter. Of course, if it is long straw, it'll take longer time to get through the premix, but eventually everything goes through it. Another system is the batch system, in this case from Envitec. We also have several Envitec biogas plants with this system. And they are also connected with a big mixer, and they're also used for grass, maize, deep litter, and so on. We don't need to put the maize through the pre-treatment systems, but it's a very good biomass to lubricate the biomass through the biogas plant. So, but from 2025, we are not allowed to use maize in Danish biogas plants anymore. So we are looking into that. We'll be using a lot more grass in the future, and also more deep litter and more straw. This batch pre-treatment system has the possibility that you can continue mixing until the feedstock has the required consistency. If you want to give some extra minutes, you have the possibility in this system. Unlike the other two systems, we don't have that same possibility. And then we also have a stone trap in the bottom, which is also very necessary. Deep litter is a very used biomass in the Danish biogas plants, and mainly from cows and calf production, but also a little bit from pig production. The dry matter content can be a challenge because it can vary from 20% up to 40%, and maybe even more if it's from pig production. Chicken production. And it's often it's a combination of very long and very short straw. We try to persuade the Danish farmers to use cut straw in the deep litter, but we don't always succeed with that. Then we also have the challenge with the bodies from stones, metal, plastic, rubber tires, and wood. And I can tell you that in the Danish pig production, we have to use some toys for the pigs in the stables. So wood is very used as a pig toy. And when they bite in that several times, the wood stick ends up to be very small, and it can go directly through the slatted floors. And then it'll end up in the slurry, and we get it into the biogas plant. So that can be a challenge. Deep litter also requires long retention time or efficient pre-treatment. So some of the biogas plant with a short retention time, maybe 20-25 days, they need some very efficient pre-treatment to get all the methane out of the deep litter. But we think that deep litter is a good feedstock with high methane potential. We have about 60 cubic meters of methane per tons, and the farmers, they like to have it put through the biogas plants, because the Danish legislation says that you have to if you store it on the fields outside, then you have to put plastic on top of it to reduce the ammonia loss, and then it's much easier to put it through the biogas plant and get it in return as degas digestate. But as you can see in the middle of the picture there, that is some of the iron parts that come from the deep litter, and the pre-treatment systems don't like that kind of metal. Straw from seed grass is also a biomass that is well used in biogas plant. We have the dry matter content right after the harvest with 40 to 60%, and then we cut it with a self-propelled forage harvester, and we make it to silage. And I think the first treatment here is in the field. You have to cut it into very small pieces. It's theoretically cutting length is 6 millimeters here to the left, and it's 11 meters in the middle. And we also tried it with a towed forage harvester, and then we got more than 11 millimeters. And then it's not very easy to get through the biogas plants. And a lot of it we see also in the degas digestate, even after 40 days of retention time. So it's a big advantage to cut it in very small pieces, and also the cheapest way to do it. The mobile crusher is also used because it has a very high capacity, and you can put an iron magnet belt on it also. So if you put some deep litter through it, then it will catch some of the iron. All the stones that can be in the deep litter, and also some of them in straw, will be crushed in the mobile crusher. And that is good because that gives a few breakdowns in the biogas plants, but the disadvantage is that sharp crushed stones, they will also increase the wearing of the pumps, especially those with rubber parts. Another advantage is that you can prepare the crushed feedstock for 4 to 7 days, and that is easier to make the planning from the employed people. Our calculation says, and also the experience from the biogas plant says, that the pre-treatment cost is about 10 euro per ton, including the wheel loader to load and unload it. But this crusher can't, we still need a feed-in line in the biogas plant, but it will increase the capacity of the pre-treatment system in the biogas plant if we have put it through a crusher in Atlantis. And it also has a positive effect on the amount of straw in the degassed digestate, the next pretreatment. We have some trials here that you can see if we have it through a crusher, and with pretreatment we had 49% dry matter content, and we had 244 cubic meters of methane per ton volatile solids, and that gives us 112 cubic meters per ton feedstock. And without the pretreatment, we had a little lower dry matter content, about 40, but we had 196 cubic meters of methane per ton volatile solids, and gives us 76. But this increasing from 196 to 244 gives us 24% extra methane yield and the same retention time. So, and you can also see it on the trials here that we have almost got all the methane out of the feedstock during the 40 days of retention time that we had. The inline treatment is also a pretty new system in Denmark, and the macerator we have known for a very long time in Denmark. We use it in front of the pumps, and it also have some inline treatment, of course. But now we also see the deflaker from Gruppen or disruptor from Fuchs, and also other kinds of inline treatment. One of the advantages is that you can increase the dry matter content in the digester with 1 to 2%, and therefore you can also make a lot of more biomethane when you increase the dry matter content. Or you can also have that the digestate is becoming more thin fluent, which gives us some advantages in the fields. The trial says so far that the methane yield can be increased to about 0.5 to 1.0 cubic meters per methane per ton feedstock. So we also get more biogas out of it. The biological way of pre-treatment is to make silage out of it. And on the picture to the left, you can see straw and sugar beets that has been mixed together. We cut the straw with a forest harvester just after harvest and put it in a pile on the fields, and then we wait till we can get the sugar beets out of the ground. And then we wash them and we crush them, and then we mix it together. It could also be pulp from potatoes, sugar beets, wet grass, or other feedstock with low dry matter content. But the co-silos of straw and sugar beets makes the sugar beets stock stable also during the summer, so we can use it all summer. Normally, we only can use the sugar beets during the winter. But the mix of 50% straw and 50% sugar beets gives us a potential of 115 to 120 cubic meters of methane per ton wet feedstock. On the picture to the right below, it is the green top from the sugar beets that we are mixing together with straw. And where we have the sugar beets in Denmark, that's also a very good possibility and gives us a good feedstock for the biogas plants to mix the wet green top from the sugar beets with the dry straw. If you look at the straw in wet, when we look at straw and we compare wet and rotten straw to dry straw, we can see that the red line here is that's wheat straw, and we have the dot line here is where we have made the silage out of the straw. That means we push it through a hay buster system, and then we add some water if it's too dry, and then we make silage out of it, and it gives us an extra potential of a methane yield per tons. Also, if we have some of the discharged bales who have been standing out in the rain for 1 or 2 years, we still have about 75% of the methane yield in a bale compared to a dry bale. So they are very good to put through the biogas plants, and they are normally also a cheap feedstock for the biogas plant. When we look at the degassed digestate in Denmark, we use all the degassed digestate on the fields as a fertilizer. And when we feed in the biogas plant with about 18% in the feedstock, we have about 8 to 9% dry matter content in the degassed digestate. And it can be a challenge to reach the high exploitation of the nutrients then when we spread it on the fields. Plus, it can be a problem to get the digestate through the slurry wagons and self-propelled slurry machines also. So sometimes we would like the dry matter content to be lower than this. And the inline treatment is one solution to help us to reduce the dry matter content and also get the higher methane out. And the other system could be use some separation of the digestate and partly reuse some of it As an example, you can see we reuse 75% of the fiber fraction in the digester, and in 2 cases it gave us an increased metal yield of 1.6 or 3.0 cubic meters per ton feedstock. So we have, and then we use the reject liquid part as nutrients on the fields, and it's very good for grass fields, because if you have this very dry matter and straw, etc., laying on the top of the grass, sometimes it comes into the cows also in the feedstock. So that gives us some problems. So that is one of the challenges when we are increasing the dry matter content in the digester, that we also have a high dry matter content in the degas digestate. So we are working on that, especially with using making fiber fraction with separation. And those systems are already integrated in some biogas plants. Some have both systems, both inline treatment and also separation, and others have only one of those. And I think we're going to look a lot more into that in Denmark. So I would like to say thank you for, I hope I could give you a little bit insight in how the Danish biogas plants, what they're doing about the pre-treatment systems. So, and I would like to thank you for your attention.
Thank you, Carl. Excellent overview. Really appreciate that. As going to be around the world looking at the potential for different feedstocks, and I think Denmark has a lot of experience in that. Carl, there is a question that came in, and let me ask that one. It says, can you elaborate on the reasoning behind removing corn as an acceptable feedstock for biogas?
Because the maize is in the environmental way, the maize is not as good. I mean, sugar beets, they're using their nutrients all time until they are being taken out of the soil, but the maize stops eating the nutrients in the end of August, September, and we only harvest it in the end of October maybe. So that's one of the reasons that it's not so good. So
okay. Yep. I think I think that's been experienced in this ban has been experienced in several countries. Let me ask, there's another one. These were focused on more physical, mechanical pre-treatment, and this may be too big a question to answer right now, but what is experience with biological thermal pre-treatment?
With heating, to heat it up, is that the question?
It says your presentation was more on physical, mechanical pre-treatment. Yeah. What is experience with biological or thermal pre-treatment?
We are working on it. We are trying to put what's it called? It's not called mushrooms, but we are trying to add something into the bales to make a pre-treatment when we just have put have baled the straw. That is one of the things that are being investigated at the moment.
Maybe Carl, maybe if you when you're done, because we're going to have to move on, maybe you can try to answer that in the chat box to this gentleman.
I would like that.
That would be great. Okay, I think we do have to, in order to keep time, we have to move on. Carl, thank you again. Our next presenter is Sven Hoff. Sven is with Advanced Substrate Technologies. AST, as we're going to call Advanced Substrate, was initiated in 2014 by Sven, and he is the inventor behind 5 patents from the company. Sven has more than 40 years of work experience in development, planning, and management of cross-sectoral projects in agriculture, agro-industry, biomass, biogas, and bioenergy. And Sven is going to discuss high-tech pre-treatment of straw with ammonia. Sven, if you want to share your screen now.
With pleasure. And thank you for giving me the opportunity to participate and give my view on some of the important things. Introduction. We are Advanced Substrate Technology, and in fact, we are focused on the following activities. We're not that much focused on biogas itself, but we are for sure focusing on how to get more biomass into the biogas, get a higher gas production, And especially we are focused on how to get added value out of the degasified material. And that we do for making substrates and fertilizer products with added value. But that we'll take more on a later event. Deeply working with circular bioeconomy and partnerships, because we believe that we together get better results than if we go alone. Today it's about mixing, cutting and grinding for effective pre-treatment of biomass to biogas. This is one of our patents that have been granted. It's technology for pre-treatment of straw and other hard-to-handle biomass to be used as biogas substrate. The types we're talking about is wet or compromised straw, because we consider good quality straw to be too expensive and better used for other purposes. We can use wet and compromised straw loose or in bales. We can also use straw collected after use as winter protection in carrot production, horse manure, chicken manure, grass, loose or wrapped, or even silage. And I'm sure this one will going to be increased dramatically in the future. Of course, deep bedding from cattle and pig production, and then dry and dusty residuals from pre-treatment of cereals. There are more options, but the main thing you can see on the photos, and all of these are produced in the primary agriculture and has to be transferred to biogas plant. And in order to increase the area where a biogas plant can collect their biomasses, our pre-treatment can be on a mobile platform or stationary. We are using a mixer and cutter, which is well known from cattle farming. We use that for cutting and mixing the different biomass, and we always try to adjust the final dry matter around between 50 and 60, because that's more optimal for the pre-treatment. From the cutter and mixer, it goes to a buffer and feeder unit, and on the transfer, it passes a metal iron magnetic belt to take away bigger parts of iron. From there, it goes into a feeder to a star screen, where we can eliminate stones and other metal pieces and similar. And from there is a buffer to go to the grinder. The grinder is in fact a pellet press, or somebody call it, but we use it in a little different way. We use it with bigger openings in holes in the what do we call that, in the slice, and we use it to open up the structure in the biomass. That means to increase the surface available for attacking and utilizing the biomass content. From the grinder, we let it pass again through a transport band with metal detector. And with this band, we can add it directly in loading in walking floor trailer or in temporary store, depending on the local conditions. How does it look after grinding? You have the photo to the left. It's easy to handle. It's easy to mix directly into liquid biomasses at the biogas plant. Doesn't give problems with floating layer. So there are a lot of advantages. What's in it? Well, it makes it possible for us to utilize hard-to-handle biomass and residues. Also, low-value biomasses can be used, and some biomasses that are a problem might even be paid for to take. Essential is that we can have more value per truckload and for less transport. If you compare transporting 34 tons of grinded biomass with 34 tons of liquid cattle manure, then you have between 7 and 8 times more energy per load. So that means quite a lot in transport cost. It's easy to handle. It can be mixed directly, as earlier mentioned. It gives plus 25% more biogas or methane per ton of volatile solids. Biogas comes faster, so we can have shorter retention time, and that means totally increased capacity on existing plants. And our calculation says that we can easily increase the total output of methane from a biogas plant with 50 to 60% by using grinded biomass. There are, of course, a lot of parameters that you have to take into account, like dry matter content in the reactor, what level you want to have as dry matter in the final thicker state. But this we can solve on the next event, because that's concerning post-treatment and utilization of degas biomass. We have some experiences, and we set up a movable plant in operation in August 2018. It was a part of Horizon 2020 demonstration project called MUBIC. We treated almost 14,000 tons, and in this plant, the average dry matter was 57.8. Average percent of volatile solids was 81.5, and gas potential per ton of VS 265 to 285 cubic meter. We were taking samples out together with the biogas plant that took the grinded biomass, and in parallel with Folum, also University of Folum. So we have documentation on the figures. Later on in December 2019, the plant was moved to Danish Biofiber and Fertilizer in Nibe, the company that we were partners in. And by end of July, we have treated another 10,000 tons with a little higher average dry matter, and also a higher average of volatile solids. Again, the average gas potential is almost the same, but the variation was a little bigger. Later on in autumn 2020, this plant was rebuilt as a stationary plant and expected to treat around 20,000 tons a year, 55% of dry matter in average, 85% of volatile solids, and a gas potential of 275 cubic meter per ton VS. The effect of pretreatment is 25%. Of course, it varies, but that was what we found out together with University of Aarhus. And if you count value per cubic meter of methane, 5 DKK, right now it's higher, but not being super optimistic, let's count the 5 DKK per cubic meter. Then the added value per ton is between 129, 135, and 130 DKK per ton. How good is the economy in this? Well, the investment for one plant that have 12 ton capacity per hour is the level of 7.2 million DKK. Lifetime in full load hours, 20,000. That gives us a depreciation per ton of 30 DKK. Operation is done by one man and one loader per shift. And that costs around depreciation, inclusive depreciation, 30 DKK per ton. Electricity is not that high as we feared, so it's 7 DKK per ton, and reparation and maintenance for another 25 DKK per ton. So in total is a profit on making the pre-treatment. Another part which is in fact the combination of pre-treatment and post-treatment. It's the enzyme for treatment of grinded wet straw and similar low-value agro residuals. We take enzyme from drying of degassed fiber or from end stripping on reject liquid from separation on degassed biomass, and we suck that through the biomass in a continuous flow. This is also one of the patents that we granted. We have experiences again from the first test we made in Folum, the demo plant, which was a part of the Horizon 2020 MUBIC, and lately commercial plant with 2 units in parallel installed at DBD. The investment 1.5 million DKK and capacity per hour 3 ton. The effect on that is of course depending on the parts per million ammonia in the enzyme and retention time. But if you reduce the retention time, then you increase the capacity. But you can expect 15 to 25% increase in biogas output, which means another 35-60 cubic meter of methane per ton VS in the grinded and end-steam biomass. So in total, we have a quite high increase in production output, reasonable investment, reasonable operation and running cost. I should also have told you things about how to eliminate sand. And I'm not focusing very much on that today, because in my view, it's more inline treatment or post-treatment than it's pre-treatment, because it's very difficult to eliminate sand as a pre-treatment. That's our experiences. On the other hand, it's possible inline, but when you make the separation, and for sure it's possible when we make the post-treatment, and maybe only recirculate the liquid part back to the digesters in order to control the dry matter content in the feedstock. We're working hard on this, and we are doing a lot of development. We intend to continue. And if you have questions, you're always welcome to contact either Peter Nielsen, he's the CEO and partner in ASD, or Sven Hoff, I'm director and partner. We have different main tasks, as you can see on this slide, but any of us can answer the questions that you might have for this. Thank you.
Sven, thank you very much. Excellent overview. I really appreciate it. You're going to have your work cut out for you, Sven. There was a lot of questions that came in during your presentation. We're not going to be able to get to all of those in person here, but maybe we can start, since you did a good job. Someone was asking, and we can just clear this up, the conversion from DKK to, let's just say, to US dollars.
Well, that's something that we can manage.
Yeah, and it's about 6 to 1. Just in general terms, it's 6 DKK per 1 US dollar for that question. Let me ask a question that came in, Sven, about particle size. What is the typical particle size for the biomass prior to it going into AD? From your system.
Depending on the diameter in the dive in the compactor. And normally we go with 16 millimeter, but that doesn't mean that it's the maximum. It's for sure the maximum size of the particles.
Okay, and what? Let's see. It says what kind of grinder is used? Cutter, hammer, chain?
No, the cutter is 2 cylinders with knives, where the biomass is cut down in pieces, and then the final treatment is done in what we call the grinder. As I mentioned during my presentation, it's in fact a pellet press, but we use it in a different way so that we get it torn apart, the biomass, and that makes it easier for the methane bacteria and the other in the biogas process to utilize the potential of volatiles in the biomass.
Great. Sven, there's a lot of questions. I invite you to look at those and try to answer what you can. Thank you again for your presentation, and we have to move on to keep ourselves on time. Thank you.
Pleasure to be with you.
Yes. We're going to switch gears a bit now. The first 2 presentations have been a bit more on agricultural residuals, and now we're lucky to have Lars Nielsen, the CEO of Enzyme here, and we're going to talk a bit more about food waste pre-treatment. We know there's a lot of agricultural biomass. We also know there's a lot of food waste available globally for biogas production. As I said, Lars is the CEO of Enzyme, responsible for all business development and sales activities, and he's got more than 30 years of working experience in international biogas, and I've been pleased to work with Lars for the last several years. Lars is going to talk a bit about the pre-treatment of food waste to produce biopulp. Lars, the floor is yours.
Hello, everybody, and thank you for getting the opportunity to tell a little bit about the EcoGi pre-treatment solution. And when we are talking pre-treatment here, it means that we take inorganic waste, the contamination, that means the inorganic stuff, so we can supply a pure biopulp that can be used in a wet digester. And our philosophy is to provide a system to extract the maximum energy and nutrient benefits from the organic waste sources. And our basic tenets are we have flexibility to accept any type of packaging. That means plastic, glass, paper, or metal, and we can produce a clean quality biopulp that will maximize the gas production and provide a high value fertilizer. And we have low maintenance and labor requirements. And here you see a drawing of a standard system, and in the right hand side you can see the feed hopper where we load the waste in, and the waste can be loaded with a front end loader or with an automatic crane system. And from the feed hopper it goes with a screw conveyor up to the pulper, where we add water to the waste, and then we rotate the waste inside the pulper, and due to that rotation we'll get some centrifugal forces that will open the packaging so we get access to the food waste inside, and this organic waste will then be dissolved in the water. And then after approximately 10 minutes, the pulping time has ended, and then we open a valve in the bottom of the pulper, and the whole batch is then going down to the separator. And in the separator, we have a vertical plate with a lot of small holes where all the fluids pass through. And that means all the organic stuff and all the inorganics stays in front of the plate. And then we wash the inorganics twice to get all the fat and grease that are sticking on typically plastic. And when those two washing operations has ended, we opened a valve in the bottom of the separator, and then all the reject goes down, and with a transport at a screw conveyor, it goes down to a screw press where we press all the water out of the rejects. And then after that, you can recycle the reject as much as possible. And the fluid we press out of it will be used in the next batch. And about our system, we have a capacity typically between 10 and 13 ton per hour. And that means 250 ton a day if you run 24 hours. And that means, again, 1,250 ton a week if you run 5 days a week. And that gives you 60,000 ton a year. And if you need a higher volume, we can add more lines in. And regarding the dry matter content in the biopulp, it's adjustable, and we will typically adjust it between 10 and 18%. We have an extremely small particle size, and that allows for an accelerated biogas production. And we have a highly automated system with low OPEX, and the scatter system can be remotely with an iPad or a computer. And the need for staffing is typically 1 to 3 hours per day or per shift, depends on design and configuration. About the system flexibility, the EcoGi technology is a combined depacking and pre-treatment system. So you can just put your packaged waste in the system. And during the pulping process, the packaging will be opened and allowing the organics to be dissolved in the liquid fraction. And we have what we call low impact approach. And that means basically that we try to treat all the inorganics as soft as possible, so we keep them in larger pieces, because then it's easier to remove them in the process. If we, like some others do, should chop the waste in small pieces, it will be much more difficult to remove those small pieces. And that means that the system is able to treat and probably manage food waste from residential, commercial, institutional, and industrial streams. And here you can see some examples on food waste we can treat. In the left-hand side, you can see some cheese in metal cans. And in the right-hand side, you can see some beer in bottles. And we can put that directly into the system, and then it just to run automatically through the system. And even though that this system is developed to treat source-separated waste, we can also handle contaminated waste. And with up to maximum 20% contamination, we can run with full capacity. And here you see some examples on some contaminated food waste. And regarding the pureness of the biopulp, the system was designed to meet the demand of Danish farmers for a high quality fertilizer and the strict Denmark and EU regulations. And the pureness of the biopulp is what we call second to none. And the EcoGi system is the only food waste pre-treat system to obtain the ETV certificate. And this certificate documents the pureness and the recovery of the potential methane in the waste. And ETV means Environmental Technology Verification, and that's a global third-party verification program for environmental technologies. And here you can see some of the results from this certificate. In the first line, you can see the purity of the product when you check for all impurities in a pulp with 17% dry matters. And here you can see we have an average on 99.96% pure organics. And if you only check for plastic, then you have a pureness on 99.996%. That means, or that's because the weight of plastic is very low. And regarding the future, we expect that we will get more strengthened regulation for use of Digestate as a fertilizer in the future, and that will demand a higher biopulp purity. And in Denmark right now, we don't only measure the weight of the plastic in the pulp, we also have to measure the covered area of the plastic. And all those future demands is no problem for our technology. We are prepared for that. And every month we send samples to a laboratory that checks all the contamination in the pulp. And it's perhaps difficult to see here, but if you can see below, there's all the heavy metals, and we are far from the limits of what's allowed to have it. So that's no problem to obtain the required purity. And here you can see some examples for some plants we have installed in Denmark. And the first example here is on a waste to energy facility where they took out one of the incinerators and installed our system instead. And in the square yellow figure, you can see the receiving hall where we receive the food waste. And in this installation, we have an automatic crane system that takes care of that. And in the yellow circle, you can see the tank where the finished product is stored and ready to be transported with trucks to an AD facility. And here you can see our plant in the north of Denmark. That was a greenfield project where we built it from the scraps on a field. And in the right-hand side, you can see a lagoon where we collect surface water from the area and use that in the production. And after or by the end of this presentation, we will show you a video from this site where you can see how everything runs. And here you can see our newest plant in Denmark. It's situated near Copenhagen. And here we have 2 lines installed because we need to treat more than 100,000 tons of food waste from the Copenhagen area every year. Yes, and if you have any questions, please write them in the chat and then I'll try to answer them.
Lars, thank you very much for the presentation. I have been able to personally see several of Lars' plants, and I can attest to what you saw in the video. Lars, we had a couple questions. We got to be quick on these. The total plant electrical consumption. Can you speak to that a bit?
Yeah, the electrical consumption is approximately 18 kilowatt hours per ton of treated waste.
Okay, great. And then someone was inquiring about who the Pulper Manufacturer is.
That's our own design. So we don't produce it ourselves, but we have a sub-supplier that produce it after our drawings, according to our drawings.
Great. And then I'm gonna try to answer this one, Lars, and you correct me, but someone asked about what we mean by contaminated waste. Here, when we talk about contamination, it's just the contamination of the inorganics, the plastic, the metal, the glass. It's not any kind of hazardous or toxic type of waste. So, Lars, I think we have to leave it at that. And I would invite you to go in because I know there are other questions in the chat room that people would love to get an answer to. Thanks again for your time. We're going to move on now, and Torgil Magard with Landia. Torgil has 25 years of experience in the biogas industry. Started at the operational engineer in a biogas plant in Denmark, then moved on to project management, and in his role with Landia, has been working on the sales of pumping and mixing solutions for the biogas industry worldwide. Landia is a very recognizable name for those of you in the field. And Torkil, I'll turn it over to you. The floor is yours.
Hi everyone, I'm Torkil Magard. I'm the sales director of Landia, and a very brief introduction to our company. We are a Danish company. We are producer of pumping and mixing solutions for different industries, among them the biogas industry. We have like 30 years or so of experience from the biogas industry worldwide. And today we have installations on 300 to 400 biogas plants all over the world. So we have a very large number of references. We produce everything at the factory in Denmark, meaning we are in total control of the quality, and we have relatively short delivery time, and we also keep all the experience in-house. The company is almost 90 years old. You can see the inventor here. And so we have, during these 90 years, been going from very, very local to being a global company. We have own companies in Germany, in the UK, in the US, and we also have a sales office in China. And in other parts of the world, we work through distributors or key accounts. The business sectors that we are active in are agriculture, which is somehow related to the biogas industry. We do a lot of wastewater, municipal and industrial, biogas, waste to energy, and we also active in the food and in the fish industry. But all the industries that we're working in is mainly taking care of waste products. If we look at the biogas sector, as you're probably aware, there are many different types of biogas plants or anaerobic digestion plants. What we are focusing on today in this presentation is the farm-based, but we also do equipment or solutions for wastewater, AD, industrial AD, food waste, and waste to energy. We are part of an industry with a high focus on climate change and carbon emissions. And this is very much in line with how we think. And it's an industry with a huge potential. I think we can all agree on that. Our solutions for biogas plants in general is that, as I said, we are supplying mixing and pumping solutions. And we have equipment for the entire biogas plants. What you see on the left is like a general design or of a typical biogas plants. And we have equipment for the reception tanks. We do chopper pumps that can pump and chop the liquid biomass, the feedstock that's going into the biogas plants. We have systems for mixing the digesters and the secondary digesters, storage tank. Afterwards, we also can pump the digestate to remote storage tanks. And We also do pre-treatment of different types of biomass and feedstock, including food and kitchen waste. And we do hygienization systems for byproducts for biogas systems. If we look at the reception area of the biogas plant, there are many different technologies for pre-treatment of the feedstock for a biogas plant. We try to and prefer to keep things simple. We're not offering any additional equipment, so to say. If you have a reception tank where you mix the different feedstocks, you need to have a mixing system there. You also need to have a pumping system in there. And we have just designed our equipment so it does the mixing and the pumping and the pre-treatment in one operation mode. You don't need any additional equipment. So less equipment is also reduced costs. It's important to say that we always recommend with our systems what we call wet mixing, that you mix everything up in the reception or the pre-treatment tank before you feed it into your digester. There are different reasons for that, but one is that if you can prepare a smaller batch, you can do it more efficiently. And also in the reception tank, which normally is a small tank of maybe 100 to 200 cubic meters, you can collect the majority of the sand. You can also collect like stones and pieces of metal so they don't end up inside your digester. In Denmark and in other countries as well, the feedstock has undergone a change. If you look at Germany, they used to use mainly renewable energy or renewable crops. And we also did that in Denmark, but not as big an amount as they did in Germany. Now we're phasing out crops for energy production, and also more and more biogas plants are being built. They are big plants. They use a lot of feedstock. So we see a change now from energy crops to waste products from crops. Typical, as you can see here, deep litter that is used for the bedding of the animals, and afterwards it's being transported to the biogas plant. There's plenty of it and it's cheap, but it creates some new challenges, and especially the pre-treatment, but also something we didn't see before. Now we also need a certain post-treatment after the digestion. I'll come back to that. There are several technologies for pre-treatment. What you see here is an example of a typical feedstock for a biogas plant, where we have on the left, you can see some quite large particles. On the right, you see finer particles. The particle size has been reduced. And this is all, we did this on a biogas plant where you have two identical lines, one with traditional mixing and one with the Landia mixing system with a Venturi system. And you can clearly see there's a difference. The TS concentration of the feedstock for this biogas plant is 11%. And what came out of that is that the line where you had the better pre-treatment and the increased solids reduction of your feedstock turned out to have an increase in the biogas production of 13%. This is, of course, for this specific biogas plant, not something we can guarantee in general, but it is a fact. And we had this proved by the University of Aarhus. So that's quite an impressive result. And this was achieved by a system that we called the Landia gas mix, where you recirculate the feedstock of the tank and pumping it through a Venturi. And in this Venturi, you have cavitation. That means pressure and vacuum, and that will, to a certain degree, increase the cell destruction of the fibers of the straw. In the digester itself. Actually, the gas mix system in 2007, where we did the first installation, was designed to have an external mixing system for your digesters. Because every time you have to open the digester to do maintenance or service on your mixing system, you lose biogas production. There's also a health and safety risk by opening a digester. So if you can have all the equipment outside the tank so you never have to open it, that's a huge advantage. And then later on, we found out that the recirculation of the digester content through the Venturi nozzle, where we have cavitation, as you can see here, actually increases the cell destruction, the solids particle size, and hence increases the biogas production. The difficult thing is that we cannot upfront say, okay, if by installing this, you can increase by this many percentage. This is impossible. On the other hand, we don't have any examples of the biogas production being lower than with a traditional system. Often also you can use less mixes compared to traditional mixing, because the gas mix is mixing in cycles and also in different levels of the tank. And you can see here's an example of a typical system. What you see here is the mixing system. It's actually only a pump and some nozzles, and that's all. So you can say the pre-treatment of the feedstock continues in the digester. What we have seen also after the biogas plant started to use more deep litter straw-based feedstocks, there was an increasing challenge with crust or floating layer in the digesters. And if you have mixes at the lower part of the digester only, they cannot break down the crust. The gas mix system will, with the nozzles in different levels, can also avoid or break down the crust in the digesters. A side note is that what we see in Denmark, where we have a high number of biogas plants, a high number of big biogas plants, is that there is somehow a lack of good feedstock for the biogas plants. So more and more feedstocks that some years ago were considered not to be valuable for the biogas process because they require hygienization, heat treatment before they are allowed to be used in biogas plants, are now in the market. And we also have these hygienization systems for pre-treatment and heat treatment of, for example, waste products from supermarkets, abattoirs, slaughterhouse, and fish industry, and different industries like that. Something that's a new challenge is in the secondary digesters of the biogas plants. Those digesters used to be very easy to mix because after the digesters, lots of the TS was removed and converted into biogas and methane. But since straw is difficult to degrade, and you actually need a very, very long retention time to break down all the fibers of the straw, we also see an increasing challenge handling straw in the secondary digesters. Many of these digesters have had problems with crust on the surface up to several meters, and we have had success of avoiding the buildup of crust and breaking it down with the Landia gas mix systems. Here is an example of a costly way of removing crust in a digester. You can see the cover is off. You have a bobcat inside the digester. Several hundred tons of material has to be removed, and during that time, you're also losing biogas production. Just to round it off, some advice based on our experience is that when you talk to suppliers for different types of equipment, being pre-treatment, pumps, mixers, all kinds of technical equipment for a biogas plant, always ask the supplier for references. Test the supplier to see how experienced are they. Do they know what they are talking about? Do they have the experience they claim to have? Also, do focus on efficiency, not on the lowest price. And never undersize pumps and mixers. You never know what tomorrow will bring. We see it here in Denmark, where the load on the biogas plants is constantly increased in order to produce more biogas, in order to produce more methane. And if you have pumps that are undersized or mixing systems that are undersized, that will create problems, costly problems, because you have to replace them with more efficient equipment. Also, if you have a little bit oversized equipment, you can typically run them less. They will last longer. You will save money on operation and spare parts. We also recommend simplicity and service friendliness as something that you should have in mind when designing a biogas plant. And also look at the supplier to consider, okay, will this supplier still be in business in 5 years? We have seen many companies in the biogas business being out of business after a few years. This is also important because the investment in the biogas plant is high. It has to be in operation for 30, 40 years maybe. So look at the supplier. Is it a trustworthy supplier? Is it a solid supplier? And also make sure that you have spare parts and service available, because your biogas plant has to run 24/7 every day. That was a very quick introduction to some of our ideas on pre-treatment, and also, of course, a little bit about ourselves.
Torgild, thank you very much, and that was excellent. We're going to have to move on to our last presenter. We're already running a bit behind. Torgild, I think there's several questions for you. Would invite you to go into the Q&A and answer those in the chat.
Thank you.
Thank you. And we're going to have to move on now. Last but not least, Lindsay Tucker. Lindsay Tucker joins us from Enzymes. Lindsay has spent her career focusing on water and waste, with a lot of experience in industrial and municipal wastewater industry. Lindsay is going to share some knowledge on the addition of enzymes to enhance food waste degradation and biogas production. Lindsay, the floor is yours.
Awesome. Thanks, Chris. So we're going to talk about using enzymes to enhance food waste degradation for biogas production. First, I wanted to give you a little intro on who Novozymes is. So we are the largest industrial producer of enzymes and microbes in the world, and have 48% of that market share, making us the market leader, with over 6,200 employees, over 6,500 patents, and over 700 products. And we're represented in over 130 countries in over 30 different industries. And what that means is that our enzymes and microbes are found in many different facets of industrial production and everyday life. So we're very experienced in the energy production industry, specifically in bioenergy, ethanol production, also in the textile industry, in detergents. And mentioned that we are an enzyme and microbe manufacturer. So these are biological particles that are helping to catalyze processes, building up or breaking down different molecules, and doing that in an environmentally friendly way, helping to get cleaner clothes with less energy, greener fuel, or higher crop yields with fewer pesticides. So now talking about how those can be used for biogas production, I'm going to look really quickly at kind of that simplified process. So if we're using, as we're kind of speaking specifically about source separated organics or municipal solid waste in this discussion, if those are entering the pre-treatment process in any sort of different separation units, you're also normally in kind of the traditional method, add in water, and you'll separate out liquid and fiber, with the fiber with the fiber fraction then going to either incineration or a landfill, and that liquid fraction going towards biogas production. But if you add in enzymes, then you're able to increase that liquid fraction, thus increasing the amount of biogas produced, as well as reducing the fiber fraction that's needing to be sent to the landfill. So I've got a quick video here that should help describe that a little bit more. Hopefully that there are not any issues with showing it.
Roughly 1/3 of global food supply is wasted every year. That's more than 1.3 billion tons of food each year. While we can all agree that food waste must be minimized, energy recovery is a promising alternative that can be generated from otherwise wasted food. Having proved an excellent substrate for anaerobic digestion due to its biodegradability and high methane yield, food waste is becoming a more and more attractive feedstock selection for biogas plants. In this video, we will demonstrate how to unlock the full biogas potential of your plant using Novozymes enzymes for food waste pretreatment. Using lunch leftovers from our own canteen and households, we have collected and blended a small batch of food waste for this lab experiment. 3 identical samples are produced from the blended food waste batch. 1 sample is treated with a small dose of Novozymes proprietary enzymes. Two samples, one with enzymes and one without, are incubated overnight to mimic a pre-treatment buffer tank in full scale prior to digestion. At first glance, it is easy to spot the differences between the raw food waste and the 2 incubated ones. By gently shaking the bottles, it appears that the sample treated with enzymes has a better solubility compared to the untreated sample. The raw food waste cannot be poured and must be physically extracted. In full scale, this means that plant equipment will need significantly more energy and water to mechanically process raw food waste without any incubation time. Turning to the incubated samples, only the one treated with enzymes can be completely poured. Physical extraction will have to be used to assist the untreated food waste. Mixing and pumping also becomes a challenge when viscosity is high, as is the case for the untreated sample. Finally, both samples are poured through a sieve to demonstrate separation properties. Clearly, the enzyme-treated sample displays better separation of both organics and inorganics, which not only implies more biogas production, but also less reject for disposal. In summary, pre-treating food waste with enzymes from Novozymes yields several benefits to food waste operations. Lower viscosity means better processability and less wear and tear on plant equipment. A better separation does not only result in more organic material for biogas production, but also less reject for disposal. A higher dry matter content means increased capacity in the biogas reactor and less water used. For more information, visit biosolutions.novozymes.com and learn how enzymes can make your plant more financially and environmentally sustainable.
Excellent. Well, I've always kind of thought that, a picture is worth 1,000 words, but a video is even better. So it does a really good job of kind of showing the different values of enzymes and exactly how that application can be useful for the plant operator. So let's dig into
roughly 1/3 of global.
Let's now look at some of the different kind of value points that were mentioned in there a little bit more in depth. So we talk about how enzyme addition can help reduce viscosity. So this is a chart looking at the details of that enzyme addition and how quickly that viscosity reduction is seen. So as you look, you can see that over time, you see a really quick decrease in viscosity so that it allows for that increased pumpability and that better separation. And it does start to plateau off there, but that time period allows for kind of not an extremely long incubation time being needed or for it to require a significant amount of extra equipment. And this is just again showing that same kind of snapshot of how we see, okay, pre-incubation prior to enzyme addition, you can see that the mixer isn't able to fully agitate all of the food waste within this sample. You're not getting a really complete mix, and it's clear that the viscosity is fairly high. After 7.5 hours of incubation and enzyme addition, that viscosity is decreased significantly, and you're getting a complete mix from the agitator and seeing movement throughout the whole sample. You're also seeing improved organic separation with enzyme addition. So if you look at the top left over here, talking about the percent of reject left with T equals 0, so immediately T is time, 99% of the reject is still left in the sample after enzymes are added. Over 4 hours, you're able to separate out an additional 60% of that, roughly 60%, giving you only 44% of that reject left. And that continues to decrease until it plateaus a little bit around like 16 hours here. And that's saying that you're able to solubilize some of those organics that maybe would have previously, in some other pre-treatment technologies, been brought into the reject fraction, but now they're able to be digested and increase the biogas yield and add improved gas generation. You also see how that total solids balance changes from enzyme addition. So at the very beginning, you can see that reject and liquid fraction, how the balance is higher towards the reject fraction. And as time goes on, you see that balance start to change with more liquid being present and the reject fraction decreasing. Same with the COD balance. At the beginning of the enzyme addition, the reject fraction has a higher load of COD, and that starts to shift and change as time goes on from enzyme addition, meaning that more of those degradable gas-producing fraction is going into the digester itself. And the same with the volatile solids balance. It's really echoing what we're seeing previously with both COD and the TS balance. At the beginning, that liquid fraction is much smaller, with the reject fraction being larger. But as time from enzyme addition progresses, you start to see that reject fraction shrink, and the liquid fraction grow. And something to consider when using enzymes is you do have to balance quite a few different parameters. You need to make sure that your retention time, your pH, and the temperature all are in balance so that you're able to get the results that you want. So optimal conditions, temperature up to 53 degrees Celsius, pH ideally around 5. Some of our products do have a wider pH range that they're active in though. And a retention time of 6 to 24 hours is ideal. So giving the enzymes enough time to work and do their job helps to make sure that they do a better, more effective job. And just to quickly kind of recap what we talked about already. So adding enzymes gives you visible results in pre-treatment. So not only that reduced viscosity, but improved separation of rejects, allowing you to get more biogas yield from the same amount of substrate, or to more easily process increased substrate addition, reducing your retention time. There's also the possibility that enzyme use can really improve foaming incidence or floating layers by helping to better degrade some of the matrices that cause those. And all of that kind of comes down to adding enzymes helps to increase your biogas yield. That is all I have.
Yeah, that was a great overview. And yeah, I agree with you. A video is worth a million words. So I think that was very helpful. Lindsay, a couple of quick questions that have come in. People are asking about the amount of enzymes that might need to be added and potentially what the cost of that might be? I know those are sometimes tough questions, but I'll put it out there to you.
Yeah, it's hard to answer really generally for that because it's going to be really substrate specific and specific to the exact pretreatment mix that's going on. I would say that really, really rough enzyme addition range could go from anywhere like 0.1 kilograms of enzyme to all the way potentially up to 0.5 kilograms of enzyme per ton of total solids added to the digester. But I really want to put the asterisk on there and the caveat saying that your mileage may vary with this. It'll depend on the specific mixture you have, the amount of retention time, pH, and then we also have quite a few different products that need to be evaluated, which one is going to be the best one for your application. So it's hard to speak specifically on price simply because there's a lot of different options that all come in at different price points.
Yep. I kind of figured that was the answer, but maybe whoever asked that Lindsay with some more specifics on that. Lindsay, another one was why go with enzymes versus mechanical or water or other potential solutions to some of the things that you talked about?
So I would say water is kind of the easiest one to answer. If you're adding a lot of water to your digester, you're effectively kind of changing the concentration of what you're putting into the digester, and you're reducing that retention time because you're diluting your substrate mix so significantly. With enzymes, what you're really doing is concentrating the organics that you're putting into your digester, allowing you to have a reduced retention time but get better degradation.
Okay, great. Lindsay, thank you. Cheryl, I don't know if Torkild is still with us, and if you could reactivate him. Great, Torkild.
I'm still here.
Couple of questions that came in for you. This one is actually somebody had said that mentioned that their operators say that they have some Landia aerators that have operated for 8 to 10 hours a day for the last 20 years and are still operating. The question was, is that reasonable, and could that be true?
That could be true and probably is true. Of course, they have been serviced through all these years, but it's not uncommon that we have equipment that is between 10 and 20 years old. You need to have your equipment serviced, and in this specific case, I don't know the exact plan, but I think it's in the UK, so they were probably serviced by our UK team. Yes, it's possible.
Great. Another question was regarding the gas mix system. Is there a maximum tank size that can effectively operate within?
Yes.
Okay.
There is. Again, it also depends on the dry matter concentration of the feedstock. But for a typical biogas plant, we don't like exceeding 30-meter diameter. And the ideal design is a tank that is narrower but higher. Like almost perfect. It's like same diameter as height. For example, 15 by 15 or maybe 15 by 18, something like that. But we do have equipment also in larger diameters.
Okay, great. Well, I really apologize to those questions, to those that asked questions we weren't able to get to. I'm hoping that the speakers have been able to answer some of those, and we'll do our best to actually have those questions and try to get back to you as best we can. However, I also suggest that you have all the speakers' contact information, or we'll be getting that soon, and feel free to reach back out to them. Couple of quick things, Cheryl, for me. And maybe I'm stealing your thunder, but I hope all of you will take a look at the March 24th Manure and Digestate webinar that is planned, and also another one on sustainability and methane leakage. on April 21st. These are all through the WBA and in association with Biogas Go Global. I'll also make a pitch for you to take a look at the World Biogas Association Summit. That's due to be June 15th and 16th in Birmingham, UK, and again, make the pitch for you to look at membership. Feel free, I think you've all got my contact information. You've got Biogas Go Global confirmation. I want to thank all of our speakers for spending their time today. I realize that it's always a little bit rushed and we don't have enough time to get to all the questions, but I think a lot of good information was shared. And thank you all for making the time today. Cheryl?
Thank you so much. Yeah, you said it very well. But yeah, I just want to say on behalf of the day, thank you to everyone involved in this webinar. The floor is being left open in networking mode in a second, so you can go and network and speak to each other face to face. And a recording of the event and the presentation slides will be made available on the WBA event page, and you can find details of further sessions in this masterclass series there. If you want to know more about the WBA as well, you can follow the link that John will post in the chat, or you can speak to John Hughes in the networking area. And I just want to say thank you so much. Thanks for joining us. And yeah, I'm going to transport everyone back into the networking area now. So thanks.